Hello everyone, this is the third video of our chapter 4 of the lecture notes, in which we are discussing the mathematical structure of a group, which will later on be useful to build some public key crypto systems. So if you remember, a group is a set G equipped with a binary operation delta that satisfies 4 axioms, which were: first, that the set G needs to be stable under the binary operation delta. Second, that the operation delta needs to be associative. Third one, that the operation delta admits an identity element. And fourth one, that any element of the set G needs to have an inverse. Okay? In this video, we're going to study a certain phenomena that arises from asking the following question: what happens if I take an element little g of the group G, and I start composing little g by itself many times? Okay, so what happens if I take G, compose with G, compose with G, compose with G, and so on? So this is usually denoted by G to the power n, and we're going to see that some phenomena happen in this particular situation, and this will give rise to the notion of a cyclic group. Okay, to start with, let's look at an example. So here I represent 6 complex numbers, which are all the 6 roots of unity. Okay, so 1 exponential I pi over 3, exponential 2 I pi over 3, minus 1, 4 I pi over 3, and so on. So this is the set U6, and we're going to equip with multiplication, okay, so that this becomes a group. The identity element is 1. Of course, multiplication is associative. The inverse of each element is the conjugate, right? If you multiply them between them, it gives 1. And you can see that it's stable, because if you take any two of this hexagon and you multiply them between them, it will give another point of the hexagon. Okay? And now we can start looking what happens if I take one element and start multiplying it by itself as many times. Okay, so let's start by this point here, for example, J. If I take J and I multiply it by itself, it becomes J squared. So J squared is this point here. And if I do it again, it becomes J to the power 3. So J to the power 3 is just adding every time 2I pi over 3. So it's this point that is here. Okay, and if I do it 4 times, I come back to the initial point. Okay, and 5 times here. So actually what you see is that if I start with G, the only points that I can generate by J, the only points that I can generate are these 3 points here, and I will continuously be swapping between the 3 of them. Okay, so to summarize that, I'm going to say that the order of J is 3, because it can only generate 3 elements. Okay, of course, if had I taken another point, well, the order would be different. If I take minus 1, for example, minus 1 to the square is 1. And then if I do it again, I come back to minus 1. So you see that from minus 1, I can only generate minus 1 and 1. So I will say that the order of minus 1 is 2. Now, if you've understood how this works, it should be clear to you what the order of exponential I pi over 3 is. Why? Because if you start from here, well, the second element that you can generate is this one. Third one is minus 1 here. Fourth one, fifth one, sixth one, right? And then you come back here. So the order of exponential I pi over 3 is 6, right? And in this case, because exponential I pi over 3 is 8, all the elements of the group, we're going to say that this element here is a generator of the group. Okay, so you may wonder whether this is the only generator of the group, whether I can find other elements that are generator, and the answer is yes. There is another element from which I can generate all the elements of the group, and that's exponential 5 I pi over 3, which is the same as exponential minus I pi over 3. So if I start from this point, the square will give me this point that is here, the cube will be minus 1, power 4 will be J, power 5 will be exponential I pi over 3, and power 6 will give me 1. Okay, so the order of exponential 5I pi over 3 is also 6, so this is also a generator of the group. Okay, good. So with this example, I have actually introduced to you a lot of new notations and new notions. So let me make them explicit now to you. Let me give you the explicit definition. The first is order of J. Order of J. Okay. So there are two ways of thinking what the order of J is. The one thing is you can say that it's the number of elements that J can generate. It's the number of elements that G can generate, right? But if you want to make this more precise, it's better to have a more precise definition than this. It's better to say it's the smallest integer, and smallest is very important here, n belonging to n star, such that G to the power n gives the identity element. Okay, so that's the order of an element. It's exactly what we just did in the example before. Second notion that is quite important, what we just see is generator. Okay, generator of the group, of the whole group. Okay, so it's an element, such that there are two ways of thinking what is a generator. The first one is to say a generator is an element which can build all elements of the group, right? So it means that for any element that you take of the group, there is a way of writing this y as G to the power n. Okay, so there exists an n such that G to the power n is y. Okay. Another way of saying exactly the same thing is just to say that the order of little g is the cardinality of the group. Okay. So in this example, the cardinality of the group was 6, right? Therefore, and you saw the two elements that were generators had as order 6. Okay, so that's a very simple way of saying what a generator is. And now the cyclic group. Cyclic group, also a very simple notion. A cyclic group will simply be a group that admits generators. Okay, so that's a way of saying admits generators. And not all groups are cyclic. Okay, just to give you one example of a group that is not cyclic, and then I will give you other examples. Okay, so let's look at various examples. It's very important when you're doing mathematics to have in your mind various examples when you're thinking about something. Is if you consider the integers with addition, well, there is no generators. It does not have one single element, is not cyclic. Okay, you need 1 and -1, so you need two elements to be able to build all other numbers from them. Okay, from 1 you can build all positive numbers, and from -1 all negative numbers, but you need both of them to build all numbers. So Z plus is not cyclic. Okay, let us look at a second example. If we work modulo 7, and we consider this with addition. Okay, so in this group, and let's be completely explicit. So let us do this. We're going to study the different elements. So 0, 1, 2, 3, 4, 5, and 6. So here we have all the elements modulo 7, right? And we're going to see what happens when I start composing 0 with 0. So 0 plus 0 one time. If I do it twice, if I do it 3 times, if I do it 4 times, 5 times, and 6 times at most, right? There are 7 elements, so 7 times at most. Okay, so here what I mean, this is 0 just once. Okay, so that's equal to 0. If I do 0 plus 0, it's also 0, and so on. So here, the first time that this 0 gives me the order of the element, right? So order of 0 is 1. So now let's do the same with 1. If I do 1 one time, it's just 1. 1 plus 1 is 2. 1 plus 1 plus 1, so 3 times is 3. And if we continue, this is 4, 5, 6, and 0. So the first time that the 0 appears is here. Therefore, the order of 1 is 7. Okay? Let's do again with 2. So we start at 2, and we add 2 every time, right? 2, 4, 6, 8, but modulo 7, 1, 3, 5, and 7, which is 0. So again, first time that 0 appears is here. So the order of 2 is also 7. Okay? And let me do a third one, I guess, and then you'll leave the other 3 to you. 3, then we add 3 every time. 6, 9 is 2, 5, 8 is 1, 4, 0. Okay, so I think that by now you have guessed what happens is that the order of all elements except 0, order of 3 is 7, the order of 4 is also going to be 7, and the order of 5 is also going to be 7, and the order of 6 is also going to be 7. Okay, so this is a very particular group where all elements except 0, except the identity elements, are generators of the group. Okay, so that's one example. Let's look at another example. Now, if you take z over 5z, but now we consider it with multiplication, and therefore we need to take away the 0, okay, so that it forms a group. Okay, so if we look at this group, it has, so let's look at the elements. Elements are 1, 2, 3, and 4. There's only 4 elements in this group, right? So we need to see what happens when 1 time, twice, 3 times, and 4 times, okay? And now the question is, when will be the first time where 1 appears? Because 1 is the identity element of the group, right? So 1 times 1, well, is 1 here, and it's 1 again here, 1 again here, and 1 again here. So therefore, the first time that 1 appears is here, right? So the order of 1 is 1. Okay, let's do it for 2. So I start at 2, and then I multiply by 2 every time, because now we're using multiplication. So it's 4. I multiply by 2 again is 8. Modulo 5 is 3. Multiply again is 6, and 6 is the same as 1. So the first time that 1 appears is here, and therefore the order of 2 is 4, right? Okay, let's do it for 3. We start at 3. 3 times 3 is 9. Modulo 5, it's 4. 4 times 3 is 12, so that's 2, and 2 times 3 is 6. 6 is 1. So also the order of 3 is 4. Okay. And now you would think by the previous example that the order of 4 is also going to be 4. However, this is not the case, because 4 here is of course 4, but if you do 4 times 4 is 16, and 16 modulo 5 is 1. Okay, so here's the first time that 1 appears. Therefore, the order of 4 is 2. Okay, so here it will be 4 again and 1 again. All right, already with these 3 examples we've seen so far, we can start seeing emerging some interesting properties about the orders of the elements. So let me recapitulate in a table what we've seen so far. So we've seen 3 groups, right? Groups, the first one was U6 with multiplication. The second was Z over 7Z with addition. And the third one was the inverse of Z over 5Z with multiplication, right? These were the 3 groups. And now we can also recapitulate here the cardinality of each of the groups. So here the cardinality was 6, cardinality here was 7, and cardinality here was 4. And which were the possible orders that we found for the elements? Possible orders that we found here, 1, 3, and 6. Those were the possible orders. Here only 1 and 7, and here 1, 2, and 4. Okay, so I think that if you look at this, you can see emerging some relation between the cardinality of the group and the possible orders. And this, let me pause for a second so that you think about it. Well, here I think it should be very clear that the possible orders are in fact all the possible divisors of the cardinality of the group. So for example, 7 is a prime number, therefore the possible orders are only 1 and 7, or the divisors of 4 are 1, 2, and 4, okay? And this is a result that is called Euler's theorem. So let me write it down here, Euler's theorem. Very important theorem for group theory. Okay, however, it does not work for all groups. The group needs to be finite. If G is a finite group and is also a commutative group, and it only works in this case, commutative group, then for all elements of the group, the order of G is a divisor of the cardinality of the group, okay? And another way of saying equivalently, another way of saying exactly the same thing is that for all elements of the group G, if you take G to the power the cardinality of the group, then you find the identity element, okay? And this is a very, very important theorem that we will be using very often, okay? So let me show you a few things of why this theorem is important. First, just some examples. If you take for G, if you take for G delta the group of invertible elements of Z over NZ with multiplication, okay, well, then there are a few things. So what is the cardinality of this group? How many elements are invertible modulo n? Well, you know that a number is invertible modulo n if it's relatively prime to n. So the question is how many numbers are relatively prime to n? And you know that that is given by the totient function, Euler's function, right? Phi of n. And therefore, the theorem here, and Euler's theorem, is saying the following. Euler is saying that for all elements, let's call them A, belonging to the invertible elements of Z over NZ, if you take A to the power phi of n, then you find 1. This should be familiar to you because this, in fact, is the RSA, the fundamental theorem of RSA, okay? This is RSA. The other example, even to make it, to show you how Euler's theorem is a generalization of things that you know, is that if we continue here and now you take if, moreover, you take for n a prime number, so let's call it, instead of n, let's call it p, then the group is the group, all elements are invertible, right? Then phi of n is p minus 1, and therefore what Euler is saying that for all numbers, if you take a to the power p minus 1, then this is congruent to 1 modulo p. Okay, and this is also something that you should know. This is Fermat's little theorem. Okay, so it's very interesting to see that Fermat's little theorem and both RSA theorem both can be are particular cases of a general theorem that you could only see when you introduce groups. Okay,